We have now reached a point in this course at which we can do a realistic analysis of a synchronous machine under certain circumstances. Before we of course, go on to do that in this particular lecture, let us first have an overview of what we are planning to do and what we have done so far in this course. So, today's lecture is actually being pursued after we have achieved the per unit model of a synchronous machine using standard parameters. Note that we have already completed in this course the general analysis of dynamical systems, in particular eigen analysis and numerical integration. We embarked upon the somewhat tedious job of modeling a synchronous machine. First of all, we obtained the basic synchronous machine model in the DQ frame, and then we went on to obtain a per unit model using standard parameters which can be obtained from measurements. We will of course, after a couple of lectures or 3 lectures, we will move on to understanding the modeling of excitation, prime mover systems, transmission line, loads and other components. Of course, these will not take as much time as the modeling of a synchronous machine. Thereafter, we will of course go ahead and do the stability analysis of a interconnected power system and also understand the basis of power system stability analysis tools. And of course, after we have done all the analysis, we will also think of methods to improve system stability. We will today do a short circuit analysis of a synchronous machine using the models that we have developed. Okay. So, if you look at what we did in the previous few lectures, we normally get a set of data called a standard parameter set of data. In the d axis, you have got x d, x leakage, T d dash, T d double dash, T d 0 dash and T d 0 double dash. And of course, alternatively you may be given, instead of 2 time constants, you may be given this what are known as x d dash and x d double dash, but they are all interrelated. So, you could be either given the first set of data or the second set of data or both. On the q axis, of course, you have got x q, t q dash, t q double dash, t q 0 dash and t q 0 double dash. In lieu of 2 of these time constants, you could be given the what are known as x q dash and x q double dash. Okay. We also of course, will be given the stator resistance, which usually is very small. In some cases, we may even be able to neglect it. Recall that in the previous lecture, I actually derived the model 2 equations in per unit form. Okay. So, we will be actually using these per unit equations to do the short circuit analysis of a generator. So, before we do that, let us look at the standard values of or rather typical values of standard parameters. For example, synchronous reactance, in fact, we are going to give some names to all these parameters, x d in per unit. Remember that we can, if we are working in per unit, we can interchangeably use L d and x d. That is, L d in per unit is the same as x d in per unit, and so on for all the reactances. So, synchronous reactance in per unit for hydraulic units is lower. You look at this, x d is 0.6 to 1.5, whereas for thermal units it can be quite high. It is almost 2.3 per unit. We shall of course see the implications of having such a high synchronous reactance later when we discuss excitation systems. X q, of course, in hydraulic units are of course salient pole units, whereas thermal units are round rotor, have a round rotor. So, you will find that the effect of saliency is not there in thermal units, or saliency is not manifested in thermal units. There may be a little bit of saliency, because the field winding is housed in slots which are basically in the quadrature axis. Okay. So, if you look at even a round rotor machine, the field winding is housed in slots on the q axis. Okay. So, this does not look very round, but anyway, I hope you get the idea. So, your field winding is effectively wound if you look at it in a 3D scale. So, your field winding is in fact wound in this fashion. Okay. So, a field winding is wound like this. Okay. So, in this axis, q axis, even though it is notionally a round rotor machine, you will find x q slightly less than x d even in a round rotor machine. Okay. So, you will rarely find a machine which has x d equal to x q. Okay. You will not find such a machine. Of course, in a hydro generator, there is actually a proper salient pole, and field windings are concentrated and wound on the pole. Okay. So, you will find a very distinct kind of x q will be very distinctly less than x d. Okay. The quantities x d dash and x d double dash, x q dash and x q double dash are called transient and subtransient reactances of the machine. Okay. Now, you will find an interesting feature here, that one of the parameters is missing for the hydraulic units. Okay. So, x q dash in fact is not given for the hydraulic unit. The reason is that synchronous machines which are driven by hydraulic turbines, normally salient pole machines, can be represented very well by just one damper winding on the q axis, because of which we need not. So, your transfer functions, psi ds upon psi qs upon I qs is only of first order. So, you do not really have to define the time constants t q dash and t q 0 double dash, or alternatively you do not have to define x q dash and t q 0 dash. Okay. So, one set of parameters reduces, because you can represent the generator driven by a hydraulic turbine by just one damper winding on the q axis. We will of course, later on see how you can have a lower order machine model, how you can actually derive a lower order machine model from the synchronous machine model which we already have. So, hydraulic turbines in fact are an example of a lower order model of a synchronous machine. So, hydro turbine driven synchronous generators are examples of lower order synchronous machine, they require a lower order synchronous machine model. So, you can look at, so T D 0 dash and T Q 0 dash, T D 0 double dash and T Q 0 double dash are in fact called the open circuit time constants. Okay. Why they are called the open circuit time constants is something we will discuss in this class itself. So, we will just hold that discussion for some time in the background, we will have it a bit later. One thing you notice is that the field time constant, what is known as the open circuit field time constant T D 0 dash, can be very large, in some cases can be as high as 10 seconds. That is of course, because the resistance of the field winding is extremely small. Okay. So, you find that the time constant associated with the field winding, in fact, this the transient open circuit time constant can be quite large, and we shall see why that is so a bit later. Okay. Why it is called so. The stator leakage reactance of course, has a range 0.1 to 0.2 both in hydro turbine driven machines as well as thermal units. Stator resistance of course, is very small. Okay. Of course, T Q 0 dash again, as I mentioned some time back, in hydraulic units, generators connected to hydro turbines, one parameter is missing, because synchronous machines in a hydro turbine are modeled by a lower order model, just one winding, damper winding on the q axis. Okay. Now, what we will do is do a simple example in this particular lecture, which uses model 2. Okay. I will write down model 2 again in this class, and uses the data which I have shown here. Okay. What we will do is, we will consider a round rotor machine. So, we will use 2 windings on the q axis a field winding and a damper winding on the D axis, in addition to the DQ0 windings. Okay. So, we will take a synchronous machine, okay, which is running say at the base speed or the rated speed. Base speed is usually the rated speed. So, let us say omega is equal to omega base speed. Okay. Let us assume of course, the speed is maintained constant in this particular study. We will of course, do a study of electromechanical transients a bit later in this course, but right now you assume that your speed is constant. Okay. So, you have got a machine which is rotating at a constant speed. The machine initially, the field winding is say short circuited, that is no voltage is applied. Okay. And what we do at time t is equal to 0, we apply a voltage in the across the field winding. Okay. So, what I have done is, we have a situation like this. So, to apply a voltage V f on the field winding. Okay. So, if you apply a voltage V f on the field winding, of course, remember the current according to our convention comes out of this dot. If you apply a voltage V f on the field winding, you will of course, some voltage will start getting induced on the stator winding. So, what we will do is assume that the stator winding is open circuited. We have in fact done this analysis before. We did the steady state analysis of this system before. We have seen this if we apply a voltage to the field winding where the stator is open circuited, you will find that after the voltage which is induced on the stator winding, for example, VD. Okay. In fact, we found that VD is equal to 0 and VQ turns out to be omega, which is omega B in this case, into MDF by RF into VF. So, if you recall what we have done in the previous class, instead of talking in terms of VF, we shall now be talking in terms of the voltage induced on the stator winding if VF is applied. Okay. So, remember we will call this of course EFD. So, under open circuit conditions. So, this is open circuit conditions. Okay. Now, the equations of a synchronous machine under open circuited conditions can be given by putting I is equal to 0, but we will not really do that, because after we finish our analysis of an open circuited machine, we shall also short circuit the machine. Okay. So, what we will do in fact is represent the machine under open circuit as if it is connected to a very large resistance. We do not actually set the put the condition I d is equal to 0 and I q is equal to 0 and I 0 is equal to 0, but we put in fact a large resistance across the machine. So, let us consider a machine which is connected in star. So, the machine stator windings A, B, C are connected in star to a load resistance R L. Okay. Now, R L is very large for under open circuit conditions and equal to 0 under short circuit conditions. Okay. So, we will formulate the equations once for all under these situations. Okay. So, what I will do is not we have already written down model 2. Okay. What I will do now is write down these equations in a kind of a state space form. In fact, it is the state space form. So, psi d, psi q, psi f, psi h, psi g and psi k is equal to a matrix A into psi d, psi q, psi f, psi h, psi g and psi k plus, let us call this A 1 plus A 2 into I d I q, okay, plus B into V d V q, and what are the other inputs? E f d or E f d, V d and V q. I mean, you can of course shuffle around here. A 1 and A 2, of course, an implicit assumption is that this machine is operating under balanced situations. So, 0 sequence voltages, currents, fluxes are all 0. Okay, so, the 0 sequence does not come in this equation. Okay, so, it is even connected to a balanced load. Okay. Now, remember here that V d V q, since I have connected a resistance, is nothing but R L 0 0 R L a star connected resistance is there here. Okay. It is easy to show that if you write out the voltage and current relationships, you can easily show that in fact, V d and V q are related to I d and I q like this. How do you do it? Well, you take V a, V b and V c, and that is equal to and apply a transformation to the dq frame. Okay. So, you will in fact get this relationship here. Okay. So, this is a relationship you should keep in mind. We have these relationships, and of course, we also have an additional relationship V d V q themselves can be written in terms of R L and I d and I q. So, actually this portion can be subsumed in A 2. Okay. So, these two variables can be subsumed in A 2. Of course, if V d and V q, if there was of course an independent voltage source, okay, at the terminals of a synchronous machine, then of course, you would have to define V d and V q, but as I mentioned some time back, V d and V q are in fact having are related to I d and I q. Okay. So, what we will do now is write down these matrices which I have defined some time back. A 1 now A 2 is minus R A minus R L 0 0 minus R A minus R L 0 0 0 0 0. This is multiplied by omega b. So, what I have done is actually of course, subsumed this V d V q into I d I q because they are related. Okay. So, that is why this R L is appearing here. Okay. These in fact equations are in per unit. So, that is an important note which you have to make. Now, this B matrix which relates all the fluxes to E f d. Now, the only input here is E f d. Remember now, in this particular study, we are, I will call this B 2. So, this is relating flux psi to E f d. Remember, E f d is the voltage, is the steady state voltage which appears the line to line voltage which appears across the stator terminals if connected in star, if Vf is applied at the field winding, and this is of course in steady state under open circuit conditions, and of course EFD is in per unit. Okay. So, these are my equations. So, what I will do is do this step change in field voltage and show you the way the system evolves. Okay. So, what I will show you now is a program which is written in Scilab. We of course recall that we have used Scilab in the previous examples when we are doing the analysis of dynamical systems. You can also use MATLAB or any other software. In fact, you can write your own programs as well. So, I will of course, in the interest of saving time, show you a simple program written in Scilab. So, you need to pay attention to what I have written here. So, this is the program. So, this is an eigen analysis of an open circuited generator. In fact, it is an analysis of an open circuit generator. The radian frequency, electrical frequency is 2 pi into 50. The speed of the machine is also the same. The parameters of the machine, I have entered them. I just showed them to you some time back. Only difference is of course, I have changed the time constant to 5 seconds because as I shall show you, the system settles down faster with a lower time constant. So, we do not have to simulate for a very long time. So, that is the only change, but I am using otherwise the parameters which I just mentioned to you in the previous slide, just showed to you in the previous slide. Remember that I have been given the reactances x t dash, x t double dash, x q dash, x q double dash and open circuit, so called open circuit time constants. You can get the time constant T d dash and T d double dash by using the relationship which I had given you some time back. Remember that T d dash and T d double dash are related to T d 0 dash, T d 0 double dash and x d dash and x q dash and x d. Okay. So, the formulae which allow you to do that of course, are these. In fact, this is continued on the previous line. So, T d, so we get these values of T d double dash and T d dash by solving the quadratic. Okay. Now, similarly, you can find out the values of T q dash and T q double dash from x q dash, T q 0 dash and T q 0 double dash using these formulae. We have of course done this relationship in the previous class as well as the lecture previous to that. So, you can just refer to the formulae. So, I have written down of course, the state equations. Note that the states are these. 0 sequence is totally decoupled. So, it is not considered here. In case it is not visible, I can increase the font. We will do that. We will just increase the font size after selecting everything. So, I will just increase the font size to 24. So, it becomes a bit easier to view. So, we go back to show this again. So, I have programmed the matrices A1. So, A1 is this is A1, A2, B2 and A3. Okay. So, this is of course written in the Scilab syntax. Now, if I want to of course get these equations in pure state space form, remember that the way the equations are written are these. So, psi dot is equal to A1 into psi plus A2 into I is nothing but the vector of ID and IQ plus B2 into EFD. Okay. So, if I want to actually get this in pure state space form, I will write it as A into psi plus B 2 into E f d by substituting I in terms of psi. So, A will be equal to A 1 plus A 2 into A 3. Okay. So, we can get the eigenvalues of A, the matrix A. Remember, it is a linear system. If in fact, the speed dynamics are neglected, then it is absolutely a linear system. Okay. So, if we in fact, we can also compute the steady state. If I want to know the steady state value of fluxes after the step has been given and we wait for long enough time, you can set this psi dot is equal to 0 and get psi in terms of E f t. Okay. So, in fact, if E f t is 1, let us assume that the voltage which is applied at the field is such that E f d eventually is 1 per unit. Okay. So, E f d if it is assumed to be 1, that is what this says, steady state value of variables with E f d is equal to 1 is simply equal to psi will be equal to minus of A inverse P 2. Okay. So, that is what is shown here on the screen here, that the steady state values. Of course, the steady state values are something which we would like to know, but the main aim of the study is to obtain the transient behavior of the machine. Now, to obtain the transient behavior of a machine, you do not actually have to simulate the system. So, what we will do here of course, is not simulate the system using a numerical integration technique, but since these are linear equations, that is psi dot is equal to A psi plus B 2 into E f d, you know that psi of t is nothing but e raised to a t into psi of 0 at the time 0. We will assume all the fluxes are 0 initially. So, this vector psi will be 0 plus the convolution integral 0 to t e raised to a t minus tau into B 2 into E f d d tau. Of course, remember that E f d and B 2 both are constants. Okay. So, we can analytically obtain if you actually evaluate this will come out to be we will rewrite it on another page. Psi of t is nothing but e raised to a t into psi of 0 plus, or rather it will be minus of a inverse a 6 by 6 identity matrix minus e raised to a of t into B 2. So, this is the time response. Remember of course, that a is nothing but e raised to a t is nothing but we have done this before p e raised to p inverse, where p is the eigenvector matrix, is the right eigenvector matrix, and this is nothing but lambda 1, a diagonal matrix containing the eigenvalues along its diagonal elements. So, this is what this is. So, e raised to is nothing but n t. Suppose the n eigenvalues of a n by n matrix, then this will be this. Of course, we assume here I am assuming that the matrix A is diagonalizable. In fact, it is, as we shall see in a few moments from now. So, if you look at the program, it actually evaluates this. It evaluates e raised to a t using this command. Okay. It's gone on to 2 lines just because we have increased the font size. So, actually this statement is continued here. So, you just continue this statement right up to this point. Okay. So, we evaluate x is in fact psi here, psi is the states, the state psi. So, e raised to a t into the initial condition of the states minus A inverse I, the identity matrix, into e raised to a t into B 2, okay. And EFD of course is 1. So, I have not written it down. So, EFD is an input which is equal to 1. So, after I do this analysis, I can get the values of ID, which is nothing but the matrix A 3 into x, the first term of A 3 into x. Similarly, I can get VD, VQ. Once I get VD, VQ, ID, IQ and the states, all the states, you can also evaluate the torque. Of course, if it is an open circuited machine, we expect torque to be 0. Remember, of course, since this is a open circuited machine, we have taken RL is equal to 1000. Okay. So, what we will do is run this program, we will quickly run this program. So, what I will do is execute this program. So, it takes a little bit of while because we are simulating this program for 30 seconds. Okay. Remember that I am not doing any numerical integration of equations, I am directly evaluating the time response obtained analytically from the using the eigenvalues and eigenvectors. Okay. So, it has done this evaluation of the time response, but before I go ahead, let us look at the eigenvalues of this matrix. These are the eigenvalues, it is a stable system. Since all the eigenvalues are negative. Okay. We can proceed further, but I think we can take this up in the next class. Of course, we have not gone to the point at which we will take our do our short circuit analysis of a synchronous machine. In fact, that is the next step. We will in fact, we are first exciting the synchronous machine by a step change in the field voltage. Thereafter, once it reaches steady state, we will give a short circuit to the machine. We have in fact not completed our analysis of a short circuited generator. We will in fact look at this program again, rerun this program again and have a look at the eigenvalues, have a look at the time responses and see whether it correlates well with what we think should be the response. Okay. The important point is, of course, once the transient settle down, we should come to a steady state which has been predicted already 2 lectures back. Okay. That is the steady state analysis of a synchronous machine. So, after the transient dies down, we should come to the corresponding steady state values. Okay. Now, one important thing which I intended to cover in this lecture, we will do that in the next one, is to understand why the time constants which are mentioned here, T d 0 dash, T d 0 double dash and similarly T d dash, T d double dash are known as open circuit time constants. And that is something, of course, we have not discussed in this class, we did not have time for doing it. We will do it in the next lecture.